So what do you think is gonna happen? Is it gonna burn or is it gonna light up properly? Yeah, I'm taking a video here and it's gonna probably light up properly, but let's see. I'm plugging in. And I'm switching it on. A series resistor will always protect an LED from burning. I have a simple circuit which a resistor is connected in series to an LED. And you can even plug this in the wall plug and the resistor will protect LED, provided that the resistance is large enough. I usually like to use a wall plug like this, especially because of the power switch on the right. I don't have to hold any component in place. If something happens, I can press and run away. And I'm switching it on. So it's lighting up proper. No. Oh. Holy God, my wife is definitely gonna kill me. Look at that. Oh my God. Look at the LED. The resistance, oh, it's here. And my fuse blew out as well. There it is. It didn't go well. Probably the resistor is not the only thing that ensures the stability. So it seems that we must investigate why this is the case, because both LED and resistor has exploded. This means that both of them exposed to a high level of current. Also, our 16 amp fuse has broken. The current must have been exceeded 16 amperes. Our resistor got extremely hot such that the resistance value reduces and lets extremely high current pass through the LED and resistance at the same time, and everything exploded. The most important thing about an LED is to know its operating point. That means its Q point. The operating point of an LED can be found by intersecting the voltage versus current curve of that LED with the line that comes from the KVL from the circuit consists that LED. What I mean is that we first take the KVL around the circuit and that will give us a line. Then we can locate that line onto voltage and current characteristics of the LED given by the manufacturer. The point where they intersect will be the current through the LED at that voltage. So here's a data sheet that I found from the internet for a blue LED with 5 millimeters of diameter. As you can see, the continuous forward current at room temperature is around 20 milliamps. This means that when this LED is operating at normal conditions, this will always draw at most 20 milliamps. So as you can see, this LED requires at least 3.2 volts to output at 20 milliamps. But we typically consider a value between the maximum value and the typical value, like 3.5 volts or something at 20 milliamps. But the most important data is here, which is the voltage and current rating, the forward voltage versus the forward current. And as you can see, the forward voltage and the forward current characteristics are given as a logarithmic scale, and here around 3.5 volts we see that the LED current reaches 20 milliamp, because above, remember, it actually provides the voltage typically around 3.2 volts, but is between 4 volts and 3.2 volts. That means 3.6 volts would be expected from this LED to work with a maximum level of light intensity. And here you see the relative luminous intensity with respect to forward current. If you have 20 milliamps of forward current, you will see 1.0 relative luminosity. That means the maximum relative luminosity that you can get from the LED. This is the maximum light that you can get from the LED, which happens at 20 milliamps. This is another LED from Vishay, blue LED at 5 millimeters again. And as you can see, it has actually a forward voltage typically 3.9 volts and maximum as 4.5 volts. This is kind of a little bit higher than the previous one, and the forward current is again 20 milliamps. So we would expect to find the forward current, forward voltage characteristics here like this. Around, as you can see, around 20 milliamps it requires 4 volts. We can generate an average of the typical voltage. For example, this typical voltage 3.9 volts and this one was 3.2 volts. So if we average them, we will get around 3.55 volts. So this is actually expected. We expect our LED to work around 3.55 volts if we are using a blue LED. So here's our circuit. The root mean square, that means the RMS voltage, which we measured by our gauge, as you can see here. And this means that it will have around 312 volts of peak-to-peak sinusoidal voltage, but that is equivalent to a 226 volts DC in a circuit. So that we can directly consider this as DC 226 volts source, and it will provide a DC current with an RMS value that is around 18.83 milliamps. This current will pass through 12.33 kilo ohms, but if we can also omit the part after the comma that will actually provide us a large current result. This large current result will make us cautious because the power level would be accordingly 4.254 watts. So this is the most important parameter here because we have to choose our resistor according to this power level. The power rating of our resistor must be higher than this value. Otherwise, we will again burn the resistance. So this is why at first try our resistance has burned because it has a low power rating, much lower than 4.25 watts. If we take the KVL around the loop, this will be the IV characteristics that we can get from the KVL equation, and this provides a line. For example, we can find the intersection point of our line with the current axis by giving the voltage 0 volts. That will provide us as 18.83 milliamps, and that is around 18.8 is around here. And what should I do next is to provide another point where actually this line crosses with the voltage axis. That is, when the current is 0, our voltage will be 226 volts RMS. And that would be probably, if I take this scaling into account, this voltage must be something like this. And this is the Q point of our LED, that is 3.5 volts to 18.8 milliamps. For the second one, if I plug the same values, for example, this is the point, probably 18.8. This means 3.6 volts is actually my average operating point. So this is how I determine the operating point of an LED with a resistance value. If I change the resistance value, I will change the slope of this circuit. If I increase the resistance value, the slope will decrease. But if I reduce the resistance value, the slope will increase, as you can see here. And like that. My voltage increases, the current increases. What happens at this point is an explosion. Eventually, when the resistance is way too low, and I hit this point and an explosion happens again. If I build this circuit and plug into the wall plug, it won't explode and probably light up properly. What I have to do now is to check whether I have a 12 kilo ohms of resistance with at least a power rating of 5 watts, which is larger than 4.254 watts. Unfortunately, I couldn't find 12 kilo ohms, which is exactly 5 watts or higher. And if I connect a 15 kilo ohms to 10 kilo ohms in parallel, it will add up to 6 kilo ohms. And that means I can connect these two parallel networks in series, which adds up to 12 kilo ohms of resistance in total. At the same time, each parallel network will have 4 watts of power rating in total, because when you connect resistors in parallel, you must sum their power ratings, because the current will be distributed among the resistors according to current division rule. Tie them together. Never tie thick metal terminals with your bare hand. Don't be like me, be wise, just solder. The long story short, each parallel network will be capable of 4 watts of power, but there will be only slightly over 2 watts of power consumed in each. As a result, the LED will light up and probably not burn.